In this lecture, we continue to discuss on elliptic partial differential equations. We have already discussed about methods like point Jacobi and Gauss-Seidel. Now, we will go ahead and try to discuss about other methods and also methods which are implicit in nature. So, the methods that we have already discussed about are essentially explicit methods, while the ones which we will discuss now will also include implicit methods. To begin with, we have a scheme which is called as the line Gauss-Seidel iteration method. So, if you look at the scheme, what we have essentially done is that we have associated the k plus 1th iteration levels to values of the function corresponding to grid points along a specific line. So, if we look back at our stencil looks like this. So, in general, when we have explicit formulation, let us say point Jacobi, then what do? We obtain f I j k plus 1 by doing f I minus 1 j at k plus f I plus 1 j at k, f I j minus 1 at k and f I j plus 1 at k. Now, if you choose those functional values or those grid points functional values which are aligned along the x direction, then you would have these. So, if you bring them all to the left hand side and assign an iteration level of k plus 1, then this is how it will look like. Because this factor 0.25, of course, will go and multiply this f I j on the left hand side already, and then if you transpose the terms, this is how it will look like, and then the remaining terms will be coming from here, the points which are available along the y direction for j plus 1 and j minus 1. Only additional thing is that we are following the Gauss-Seidel approach, and therefore, we are making use of the latest available values, and therefore, we have a k plus 1 value associated with the I j minus 1 point, because you would have swept that point before you came to the point I j. Now, when you come to I j, you are solving the values of f I minus 1 j, f I j and f I plus 1 j simultaneously. So, that would mean that this is an implicit algorithm. And as you can understand that this will have a tri-diagonal structure, because we have 3 unknowns in a line. All these 3 are unknowns and they are lying on a particular row. If you look at the matrix form of the equation. So, as though you are trying to sweep the domain and cover all the interior grid points by writing down a system of linear algebraic equations which can be expressed in a tri-diagonal form. That would be the structure of this problem. Now, if you do so, you would have an efficient algorithm to work out the problem, which we talk about as the tri-diagonal matrix algorithm. But before we go into that algorithm, let us once again look at the structure of the problem as we have laid down in this case. So, what we are trying to say is that we are taking the grid points row by row and we are trying to solve them simultaneously and sweep the domain. So, if this is the west boundary, this is the east boundary of the domain, you are trying to solve for all the interior grid points for a given j simultaneously. So, that is what the line Gauss serial iteration method is all about. And why is it called as an iteration method? Because if you solve for all the values in one shot and then move to the next row and then solve them again that way, and you run through the entire domain once, you may not be able to reach a converged value of the functions that way in one such sweep. You may actually like to do the sweep of the domain in a different manner in the next round. So, here it is a row wise sweep. Next time you may like to do it as a column wise sweep, and that could be good for certain problems which do not have any preferential direction involved as a part of the physics of the problem itself. However, continuing with the row wise sweep over different iterations could help in problems where inherently the problem has a directional bias. That means, you know a priori based on the physics of the problem that the variations are going to be predominantly happening in the row wise directions. So, then there is a sense in doing it row wise. So, the main question to pose in this case is that if we now understand that tridiagonal matrix algorithm will be a very useful tool to use, then how does this algorithm function at all? So, let us try to discuss on the nature of the tridiagonal matrix algorithm. So, that we have. So, let us try to write down a system of linear algebraic equations and then try to express them in a matrix form. So, let us say that the equations look like this. The variables are given by x 1, x 2 up to say n, and then we have coefficients associated with those variables b, c, and you have known values which are on the right hand side. So, let us say this is the first equation. We will just write it in a slightly different manner. So, this is essentially a system of n linear algebraic equations, and we need to solve them simultaneously in order to obtain the values of the unknowns, which are x 1, x 2 up to x n. So, this is essentially the solution we are seeking. So, let us first write it down in a matrix form. So, how will the matrix look like? Let us try to fill up the matrix. So, we already know about the coefficient matrix, we have discussed about that. All these entries are going to be zeros, also these would be zeros, and then you have a column vector here. The column vector comprises of the unknowns. So, this is essentially the matrix representation of the equations that we have written above. So, we have to find an efficient way to solve this system. Of course, one thing that we realize is that it is a tri-diagonal system of equations. Now, we will do a few steps in order to eliminate variables from these equations, that these n equations that we have, in a systematic manner and in a progressive manner, and then try to find some recursive relations, so that when it comes to doing the computations, these recursive relations can be intelligently used in our computer codes. So, let us look at the second equation. When you look at the second equation, we will try to do some modifications in such a manner that we end up having a modified second equation, where we manage to eliminate one of the variables. So, these steps are essentially having some similarity with even steps that we do in Gauss elimination. So, what we will do is we will multiply the existing equation 2 with B 1 and subtract equation 1 multiplied by A 2. So, what does that produce for us? Let us see whether we are able to eliminate one variable from the second equation in the process. So, this is what you will get as an outcome. You will see interestingly that this term and this term would cancel out in the process, because you have a A2 B1 x1 here, you have the same things produced here and subtracted. So, you finally have one of the variables reduced, so we will call this as the modified equation 2. Also, we will give some nomenclature for these terms that we have generated. We will call this as B 2 tilde and what we write over here on the right hand side of the B 2 tilde expression also contains some tilde expressions, which we are doing for convenience, because these would help us generate the recursive relations which we are aiming to generate later on. So, you will understand more clearly later what is the motivation behind introducing these tilde expressions here. We similarly call this as C 2 tilde, and that we write as C 2 times B 1 tilde, and this as D 2 tilde So, we have completed our work with modified second equation. Let us do a similar exercise for the third equation. That means, we are going to aim for a modified third equation, where one of the variables get eliminated. So, let us first write down the equation 3. So, equation 3 as it stands looks like and we are now going to do a modified equation 3. So, abbreviated as ME3. So, what will we do in generating that? We will multiply the existing equation 3 by an expression B 1 B 2 minus C 1 A 2. We will understand the significance of this operation later. and subtracted from, and what we subtract from there is equation 2 into A 3. So, what does that produce? Let us try to write down the expressions. What you have on the right hand side is this. So, what you have achieved essentially over here is that this term A 3 x 2 times this will get cancelled with this, because you have a x 2 here, A 3 out here, and that exactly matches with this, and the bracketed term is identical for both the cases. So, you will have a simplification. After you simplify this, what you can write is and what we will do is we will call this whole expression as B 3 tilde, and that will be expressed as B 3 times B 2 tilde minus C 2 tilde times A 3, and we will call this as C 3 tilde equal to C 3 times B 2 tilde. So, this is what you have on the left hand side of the equation, and what you have on the right hand side of the equation can be written as so this whole right hand side term will be called as D 3 tilde So, we have a whole lot of modified coefficients which are expressed as tildes, and the main question to ask at this point is, are we heading towards a generalization? So, if we observe carefully what we have generated by modifying these equations, we can watch that certain recursions have surfaced. So, we have different coefficients, we have A's, B's, C's, and then we have the right hand sides D's. So, you will see carefully, if you look at the modified equations in particular, these recursive relations would work for each one of them. And now, you will understand better that how those tilde values have been indicated in each of the modified equations. So, we have indicated that how these tilde values are to be interpreted. In for all i's, A I tilde is going to be 0. It is because one of the variables is being eliminated in each of the modified equations, and that happens to be the first variable in that row. So, therefore, the coefficient for all of them are going to 0. That is why these are showing up that way. Whereas, for the other coefficients b's and c's, b1 tilde is b1, but for all the remaining i's starting from 2 to n, the recursive relation works like this, where you do not only have b, but you also have products of b I times b I minus 1 tilde minus c I minus 1 tilde into a I and so on. Similar recursion relations are indicated here for C and D, and if you look at each one of those modified equations, you will find that these recursion relations work, and that is a big convenience for us, because when we do computer programming of this algorithm, then we can recursively use these expressions for generating the modified coefficients for each and every linear equation that we have in our family. What do we finally gain out of it? We gain a significant simplification, in the sense that this way, if we keep eliminating one unknown from each one of the equations that we have, when we reach the nth equation, which should have contained 2 variables, would now have only 1 variable to be solved. And therefore, once you solve that variable, you can feed back that solution to the n minus 1th equation, which will contain 2 variables, out of which one has been solved already. So, the other one can be solved from that equation, and so on. So, you can just solve the entire system of equations by back substitution. So, that way, if we just try to formally lay down the structure by writing down the remaining equations, they would look somewhat like this. So, we can have one further simplification. If we have the b I tildes not equal to 0, then we can divide all the coefficients by b I tilde, and therefore, we could name them now as primes. So, a I prime would be a I tilde by b I tilde, which will remain as 0. b 1 tilde will be equal to b I, sorry, b 1 dash will be equal to b I dash is equal to 1. That is because all of them will be divided by b I tilde, which will give you a 1. C 1 dash will be C 1 by b 1, and for the remaining i's, that is from 2 to n, it will be C I tilde by b I tilde. Now, if you substitute the expressions for those, the numerator and the denominator, this is what you will get. And then this can be further simplified as so, this expression that we have written can finally give us an expression for C I dash, which will look like this is nothing but C I minus 1 dash, and so you now have an expression for C I dash. Of course, this holds good for I is equal to 2 to n. Then we can look at d 1 dash, which will be d 1 by b 1, and then for the other values of I from 2 to n, it will be d I tilde by b I tilde. So, what we are doing essentially over here is just using those recursive formulas in the respective places and trying to simplify. So, we now have an expression for d I dash, and this holds good for I is equal to 2 to n. Now, if you put all the things together, what have you got finally? You have modified the same system of linear equations and expressed it like this. This is the form for I is equal to 1 to n minus 1, and what you have as the nth equation looks like this. So, this is for the nth equation. So, what have we got? We have got only one variable to solve in the nth equation, which is nothing but x n is equal to d n dash by b n dash. Once you have that, you go back to the n minus 1th equation, where if you substitute I is equal to n minus 1 in this equation, what will you get? You will get b n minus 1 dash x n minus 1 plus c n minus 1 dash x n is equal to d n minus 1 dash. So, you have already solved for x n from the last equation, which will be substituted here, and therefore, you can solve for the only unknown in the n minus 1th equation, which happens to be x n minus 1, and this way you move backwards towards the first equation, ultimately ending up solving for the entire system of unknowns. So, this is essentially how the TDMA functions. So, we now realize that if we are able to have a tridiagonal metric structure in the coefficient matrix, how conveniently it could be done through the TDMA approach. We will look at application of TDMA further in later lectures. Thank you.